And good morning, everybody. Welcome back to Non-Euclidean Geometry. Plan for today is I have a quiz for you, and then we are going to try and finish this packet. Specifically focusing today on Aristotle's angle unboundedness axiom. As far as office hours go, my next office hours are on Monday after class and from 2 to 3. And don't forget you have a homework set due Monday, homework 5. What do mathematical mermaids always wear? They always wear algae bras. You take like 5 classes, you just run into your jokes again.
I know.
All right, any questions or comments before I pass out to today's quiz? In that case, two sheets stapled together. Since I asked you to show something is not a Hilbert plane, I gave you an extra sheet with all the incidents between the congruence axioms, but the actual quiz itself is just front and back of the first page. So I have. If it helps you, feel free to rip off the back page that just has the axioms. I do not need to see that. go ahead and take a few seconds to finish up your thoughts. And pass your quizzes forward, please. Your quizzes in, please. One letter, two letters, all right. All right, Steph, we need to have a conversation about how to turn it into oriented interpretation.
But you can't. That was okay. You can't just do that. You can just and he's like, oh no, we're just assuming they do it. And I'm like,
alrighty, let's come back together. So, plan for the rest of the class is I'd like to try and work our way through the rest of this packet, which honestly, the rest of this packet doesn't really have much to do with quadrilaterals, but I didn't want to make a new packet just for it, so it's getting thrown in the quadrilateral packet. So I'm going to be picking up on the page that starts at the top. The Hilbert plane is called Semi-Euclidean if blah, blah, blah. So last couple classes we've kind of looked at how to Sakari quadrilaterals, Lambert quadrilaterals, and triangle angle sums all kind of relate to each other. And they're all related through this notion of either everything's acute / less than 180 degrees, or obtuse / greater than 180 degrees, or right / triangle angle sum equal to 180 degrees. That if we're working in a Hilbert plane, then you're always in one of those three kind of sets of conditions. And I figured I'd start today off by introducing a new term called Semi-Euclidean, where we're going to say that a Hilbert plane is called Semi-Euclidean if all of its angle sums, or triangle angle sums, triangle, I should spell, are exactly 180 degrees. So in other words, if we're going to be working over a model of geometry where you know that all of your triangles have angle sums exactly 180 degrees, we can call that a semi-Euclidean model of geometry. Dr. Gerska, why is such a thing called semi-Euclidean? Well, what does semi mean as a prefix?
Kind of, that would be because it doesn't guarantee parallel postulate.
Yeah, usually semi typically means like half. So half, or kind of, like, it's something that is sort of Euclidean, but not necessarily fully Euclidean. And what I mean by say it's something that's semi-Euclidean is sort of along the path to Euclideanness, that's a word, is because we have the following theorem, which is a Euclidean plane is always semi-Euclidean. Meaning if you have a Hilbert plane in which the Euclidean parallel postulate is satisfied, or in other words, a Hilbert plane where we have Hiop, then it's always going to have this semi-Euclidean property of having triangle angle sums that are always exactly 180 degrees. Here's our proof. We already proved that. So if you actually recall, in the last packet, we actually showed that any Hilbert plane in which we have P-out, so implying that the Euclidean parallel postulate holds, automatically is going to have that its triangle angle sums come out to exactly 180 degrees. And the way we did that was by kind of combining an application of the alternate interior angles theorem, which we applied a couple of times, where if this is A, this is B, this was C. What we basically did was we formed a line through C that was parallel to AB. We said that A has to be congruent to that from the alternate interior angles theorem. B has to be congruent to that angle by the alternate interior angles theorem if these two lines are parallel. And then since angle C plus angle that plus angle blip adds up to exactly 180 degrees because they combine to give us two supplementary angles, and something adding up to two right angles. That implies that this angle plus that angle plus that angle also has to equal 180 degrees in a Euclidean plane. Where the Euclidean part that we needed was in being able to construct the line through C in the first place that was parallel to AB. And we also needed Hilbert plane properties to say that to be able to apply the alternate interior angles theorem. Yeah, that.
So Euclidean plane is a Hilbert plane plus EM?
Plus EM, yes.
Okay.
Yep. So every Euclidean plane is semi-Euclidean. The question is every semi-Euclidean plane Euclidean? I'm going to see you shaking your head a little bit.
I'm shaking my head only because I feel like that would be stupid to call it something else if they were logically equivalent.
That they're logically equivalent, then why are we calling something only semi-Euclidean and not just saying Euclidean?
Yeah, but I can't come up with a counterexample at this moment. So.
Indeed. So Megan, your intuition is spot on. Turns out to be the case that not all semi-Euclidean planes are Euclidean. Though we haven't seen any examples of Hilbert planes that are semi-Euclidean but not Euclidean because they're very hard to construct. If there was a prereq for this class that was having taken like 2 or 3 semesters of algebraic geometry, we could construct something called a Dane plane. Yes, I know, yes, Elaine, it's a very amusing name. That would actually make this work, but it turns out that outside of some very kind of niche, hard to do constructions, it's actually pretty hard to get an example of something that's a semi-Euclidean plane, but not a Euclidean plane.
Wait, wouldn't you be semi-Euclidean, but not Euclidean?
Gasp! Nathan has caught me in a web of lies. What about you? If you remember, U was the model where it's not the Poincare disk, but all points are inside the unit disk, and lines are just kind of the usual R2 lines, except we cut it off to be inside the circle. And we saw that that actually has 180 degree triangle angle sums, because a triangle in U is just the exact same as a triangle in R2. But U was also not Euclidean, certainly not a Euclidean plane, because if this is our line L and this is our point P, generally we can find more than one line that passes through P and is parallel to L. We say like and. There, I found 2 lines that pass through P and are parallel to L. Sorry, Nathan, that doesn't work as a counterexample. Why doesn't it work as a counterexample? I see.
It's not a Hilbert plane.
It's not, U is not a Hilbert plane. Yeah. U does work. I'm glad you brought that up, Nathan, because if you hadn't, I was going to. I was going to say, what about U? U does give us a model where we have this nice triangle angle sum 180 degrees property, despite the Euclidean parallel property not holding. But we can't call U a semi-Euclidean plane because it doesn't actually satisfy the conditions necessary to be a Hilbert plane in the first place. So, for instance, congruence axiom 1 is violated by it. Luke?
Oh, that's what I was just asking. Is it because it violates the congruence axioms?
Yeah, that would be like one way, like congruence axiom 1 for, not all of the congruence axioms, but congruence axiom 1, for instance, because we could say, oh, if this is our line L, then given any ray, we should be able to cut that ray off at a point, according to congruence axiom 1, to give us a segment that's congruent to L. And what if my ray looks like this? There's no way to find a point on this ray that we can cut it off in order to get a line segment that's congruent to L. I guess L needs to be a line segment. Fine, there's L. It's now a line segment. There's no way to cut this off at a point to get something congruent to L because the ray just dead ends. It can't extend infinitely far. That would be, for instance, of one of the axioms being a Hilbert plane that U does not satisfy. Yeah. If you want something that's actually a Hilbert plane and actually has triangle angle sums 180 degrees, but is still not Euclidean, that's very hard to construct. Yeah. I'm glad you offered that, Nathan. Any other questions or comments about Euclideanness or semi-Euclideanness? Well, since semi means half, I always felt like a semi-Euclidean plane should just be like a Euclidean plane. Remove half the letters or something. But, I don't think that quite works. Okay, so last thing I want to talk about in this packet is another axiom. This one being one we haven't seen before, called Aristotle's axiom for short, or Aristotle's angle unboundedness axiom, if we want to write it all out. And what Aristotle's axiom says is that given any side of an acute angle in any segment AB, there exists a point Y on the given side of the angle such that if x is the foot of the perpendicular from Y to the other side of the angle, xy is greater than AB. So what's that mean? So what that means is you give me any segment AB to start with that we're going to kind of use as our measuring stick, and any angle that is acute. So here's an acute angle. What this is saying is that the two legs of the acute angle, the two rays making up the sides of the angle, are eventually going to get so far apart that no matter how big a line segment AB I start with, I can always go far enough out on this top ray to find a point X, where if I draw the line segment going straight down to intersect the other ray perpendicularly at some point Y, intuitively, these two rays are getting far enough apart so that eventually I can make a line segment between them like this that's going to be longer than AB, no matter how big AB was to start. So that intuitively, what this really means is that the two rays of any acute angle get arbitrarily far apart from each other. Or let's even say, dare I say, infinitely far away from each other. that no matter how big a measuring stick you hand me, no matter how big a long segment AB you hand me, I can find, and given any acute angle at all, the two rays eventually get far enough away from each other that I can find some point on the first ray and the point on the corresponding point on the second ray that makes this line perpendicular to this one, so that these 2 points have a distance from each other greater than AB, at least intuitively speaking. 2 rays are getting arbitrarily far apart. So I can do this no matter how big an AB measuring stick you give me. So what do y'all think? Should we try and prove this? Steph, I see you shaking your head. Yeah, we're not actually going to try and prove that this holds in any Hilbert plane, for instance, because it doesn't. It's an axiom. So this is something that Aristotle proposed as true and said, I choose to believe this is true without offering any proof of it. What's that line?
I hate that guy.
You hate that guy, Aristotle? And you call yourself a Hillsdale student? Please. No, I'm not going to take that joke. That would be going too far. So this is something that Aristotle assumed it was going to be true, and it is true in R2, for instance, but didn't offer any proof of it. And it turns out that it's not always true. Can anybody think of a model of geometry where Aristotle's axiom doesn't hold? Luke?
I don't believe, it would not hold on the point array disk.
Why not?
Because, well, so the thing is, you could just have it where the rays can't extend far enough, so that way they get far enough apart. Because we've already shown that if you, if say you have it and you have, say the line segment is the diameter, and you have A, and you have a line, well, pretty much any point that is.
Would you like to draw a picture of what you're describing, so I don't have to try to picture it in my head? Oh, thank you.
It's a good circle.
And then, regular second, you should draw it this way.
So you're saying that AB is so long that no matter what 2 points on the rays you pick, then the...
Because if you extended it, they would be there, and I don't think there's...
So how would you have your 2 rays extend a line that perpendicularly goes from your first ray to your second ray? You sort of need like a line between the 2 rays that intersects.
Yeah, that's what I was saying, is that, once you get past here, they don't exactly have the perpendicular.
You can't make the perpendicularness even happen? I think Okay, that works. Thank you. I think an example that might be a little bit easier to kind of illustrate would be if we go back to U, where our lines are less curvy. And if we were to say something like, how's this for my measuring stick? Here's my AB, and let's say my angle looks something like this. I would say these two rays never have a chance to get so far apart that we could draw a segment from one to the other that'll have a length greater than AB on it. Of course, U and the Poincare disk, for that matter, are not Hilbert planes, so this doesn't prove anything about how Hilbert planes have to satisfy Archimedes, spoiler, Aristotle's axiom. However, it is going to be true, this is a theorem, that any Hilbert plane that has Archimedes' axiom will have Aristotle's axiom as well. And as we said, Hilbert planes without Archimedes' axiom are very hard to construct. In fact, we haven't seen any. So you can have Hilbert planes with Aristotle's axiom holding true, like R2. You can have some where it doesn't hold, like that Dane plane thing I told you about would be an example. Don't ask me to define that. I don't want to spend the next week doing that. Turns out, though, if we flip to the back page, we can actually prove, this will be our last proof of this packet, that it is possible, or that any Hilbert plane that's also a Euclidean plane, meaning a Hilbert plane with Euclid's parallel postulate, will imply that Aristotle's axiom does have to hold true. So let's prove that. To prove that, we're going to need a lemma first. And I'm not going to prove the lemma because it's a little bit tedious, but that's an interesting result. So our lemma is going to say, given any acute angle, you know what, I'm just going to draw a picture. Given any acute angle with a vertex V, we're going to let y and y prime be points on one of these rays, so that y is between y and y prime. So we have y being in between y and y prime here. And then if we kind of drop lines from y to the second ray and y prime to the second ray that intersect them perpendicularly like this. So if we drop a line from y to the second ray perpendicularly at a point x, and do the same thing for y prime to get a new point x prime, then xy has to be less than x prime, y prime. So in other words, this is true in any Hilbert plane, where if you have two different line segments on your from one angle to the next that both intersect perpendicularly like this, the points that are closer to the vertex are going to make a line segment that's smaller than the line segment formed by the points farther away from the vertex. Which feels kind of intuitively obvious, but not the easiest thing in the world to prove. So with that assumption, though, we can actually prove that in any Euclidean plane has Aristotle's axiom hold true. So first of all, here's our proof. So first of all, we're going to assume that we're going to start with some line segment AB and some angle alpha that we can work with. So we're going to assume that we're given some AB and any acute angle alpha. So I'll go ahead and draw out our AB over here. So let's see, this will be A, this will be B, and I'm not going to draw alpha quite yet. Alpha's going to appear here in a minute. But our goal is going to be to show that we can construct a line segment between the two rays of our arbitrary alpha in a way that'll make it so we can have a line segment that is longer than AB. So given our AB and any acute angle alpha, I'm going to let alpha star be angle that is complementary to angle alpha. What does it mean for two angles to be complementary? Okay. Yeah, they add up to give the same angle measurement as the right angle. So they add up to 90 degrees. So we can assume that alpha's degrees plus alpha star's degrees add up to exactly 90 degrees. And now what we're going to do is we're going to lay off an angle alpha star, a copy of alpha star at the point A, and a 90-degree angle at B. So if we go over here, let's assume, I don't know, for the sake of argument, let's assume that this is what alpha looks like. And if alpha looks like that, then that means alpha star would look like that. And so what I'm going to do is I'm going to transfer a copy of alpha star so that it points upwards from the point A like this, so that we get an angle going up from A that's congruent to alpha star. And similarly, I'm going to have a right angle going up from B in the same direction. So, we got angle alpha star and a right angle from B, and we're going to have two rays going up from that. I claim these two rays have to intersect each other. There has to exist a point C somewhere up here where these two rays would have to intersect each other. Why is that? Yeah?
We are assuming the Euclidean parallel postulate, right?
We are indeed. Well, we're assuming we're working over a Euclidean plane.
So we said that that was equivalent to Euclid's parallel postulate, which said that if we have a transversal, which we can say is AB, and two lines on the side where the sum of the angles is less than 90 degrees, then they'll meet. Two lines will meet.
Less than 90 degrees?
Less than two right angles.
Less than two right angles, so 180 degrees. Yeah, so we know that this angle plus that angle add up to something less than two right angles, because alpha star is acute since it's the complement of an acute angle, alpha. And so since these two angles are less than 180 degrees combined, then these two rays will have to intersect according to Euclid's version of the parallel postulate. Yeah, well said. So if we do this, we can say by Euclid's parallel postulate, these rays must intersect at some point C. So these two rays we get sticking out of AB have to intersect at C. So, question. What sort of angle are we going to get at the point C? Right?
It's gonna be alpha because you're forming a triangle and you know that the interior angles have to add up to 180 degrees because you're.
We know that alpha star and alpha have to add up to 90 degrees. And we know that all three of these angles add up to 180 degrees. So this angle that's left up here is forced to be whatever alpha is, forced to be congruent, let's say, to angle alpha, in order for the sum of these three angles to give us 180 degrees. So we can say, since triangle ABC's angle sum is 180 degrees, and we know that because we're assuming that we're working over a Euclidean plane, and Euclidean plane is semi-Euclidean, and semi-Euclidean means triangles have angle sums of 180 degrees. Since that's 180 degrees, and alpha degrees plus alpha stars degrees equal 90 degrees, that's going to tell us that our angle at C has to have the same number of degrees as alpha, which will tell us then that our angle at C is going to be congruent to alpha. And then now we just need to let y be any point with C star A star y, K. Get it? K. So basically, now we need to just pick a point on the opposite side of A from our point C. We're going to call y here. We know that such a point has to exist from from between this axiom 2. And then we're going to let's do that and let x be the foot of the perpendicular drawn from y to the ray CB. I know we're out of time, but this proof's almost over, and I just want to finish it because it's a nifty little proof. Better piece of chocolate. So here, this ray CB is going to go off this way. We're going to draw this segment from y over to this other ray that'll intersect it perpendicularly at some point x. Then I claim that xy is a line segment that's greater than AB. Why is that? Elaine?
Dilemma.
Oh, I erased it. It was over here, but I erased it. Yeah, our lemma said that these two line segments, since this one's further from the vertex than that one, this line segment has to be longer than that one. And what have we done? We've shown that given any acute angle alpha to start with, in any line segment AB, we can always find 2 points on opposite rays of alpha that if we draw the line between them, will give us a line segment greater than our arbitrary AB that we have to start with. And so our proof is done. All right, that's it for this packet. Just so you know, it's a turning point this semester in that we've now reached the point where when I last taught this course that the class ended because we ran out of time, and because we missed a week due to COVID and other reasons. When we come back, we're going to move into chapter 5 in the book and start looking at a little bit of history of all of the poor fools who tried to prove Euclid's parallel postulate from Euclid's first 4 axioms, and why each of them went horribly wrong. So you all have a good weekend. I will see you all on Monday.